All right, so welcome to our course in Cyber Physical Systems. And today we're going to be discussing requirements in software design as far as Cyber Physical Systems is concerned after having talked about a little bit about software engineering. So in terms of Cyber Physical Systems, it becomes even more important to have this distinction and a clear view of requirements. So, and we're going to see that we have two types of requirements. The first are user requirements, which are written from the perspective of the customer, and these are written in a natural language. So, and that presents some difficulties. Because if you write requirements in a natural language, then there can be ambiguity. There can be ambiguity, or another type of ambiguity is over flexibility. So things are not well defined, or they are too broad, they are articulated in too broad of a way, and things like that. There can also be lack of specificity in the sense that when you write a requirement, you may be mixing something about another requirement. So that lack of separation makes it harder for the developers to code it and to test it and to validate it. And ultimately, you can have lack of modularization because natural languages are inadequate for that. So in that sense, we should really look at alternatives to natural languages to specify requirements and tools that make that effort easier, i.e. not using natural languages to capture requirements. And some of these tools are graphical notations, and it could be graphical notations and mathematical representations like state type of state vector representations, state machines, and things of that nature. So requirements are written primarily as a contract. So you can view requirements as a contract between the client, whoever you're going to deliver the software to, and the people that are writing the software. And in that sense, they are structured documents that detail the description of what the software is going to do. So those are the requirements, and the focus is the client, whoever is going to use the software, and the focus are the what the software needs to do. And then you have software specifications, which are coming at it from the other way, from the developer's perspective. They're written for developers to tell the developers, the coders, how is that the software is going to be brought to life or implemented. So both of these requirements can have different parts. They can have functional and non-functional parts, and also domain-specific requirements that are important. If you think about the functional requirements, we're talking about statements of the services, the functional services that the software should provide. How should the software react to different inputs, and how it should behave in different situations. So that's the functional requirements. So what would be examples of non-functional requirements? Well, these are constraints of how well it may do these functions, because the functionality is on the qualitative side. It needs to do this, or it must not do that, but that's not on the qualitative side. Non-functional requirements layer up on top of that, or can layer up on top of that, quantitative type of constraints. So how well something is done, and how well it should comply, what type of time constraints and things of that nature. And of course, the domain-specific requirements, those come from the application. What type of domain is the software going to be operating in or serving? So when you have all this together, you have a set of documents or documentation package, which again, it doesn't need to be written in a natural language, but it should have, or it should embody, an official statement of what is required from the people that are going to implement the software. And it should specify things like external behavior, what are the implementation constraints. It should be easy to change, so that's why making or capturing requirements in a succinct manner is important, because that makes it easier to change and manage. And it should serve as a reference tool for the people that maybe later on, much later perhaps in time, are going to have to maintain this software. So it becomes an important part in the life cycle. It really becomes a tool in the life cycle of the software system. It could also characterize responses to unexpected events, so exceptions and exception handling and things of that nature. So the requirement document is not a design document. So we're talking about the requirement from the user perspective. It's not a design document. It states as comprehensively as possible what the software should do rather than how it should do it. And if at the onset you have requirements that you are able to capture faithfully, requirements at 90%, if you're able to capture 90% of the requirements, you're really doing well. You're really doing well, because it's very hard. Things come up, things change, new knowledge becomes available. So that's why it's important to be able to manage requirements, be able to change them. And if you go back to what we discussed on the IAL methodology, that is very attractive. And it can also be a competitive advantage for the people developing software and for the people that are receiving the product. So requirements for software is actually an IEEE standard, and that was first published as an ANSI standard jointly with IEEE back in 1984, but there is a latest revision or version that dates back to pretty recently of 2011. In this standard, the IEEE or the IEEE standard separates requirements into two groups. So again, what we've been talking about, client-side requirements, developer-side requirements or software specifications, and the what and the how. So that's the way to think about this. So they have what is called the C requirement, customer requirements, and the D requirement, the development requirement. So C requirement, focus on the customer, from the customer's view, what the software needs to do. D requirements, focusing on the developer, specifying what needs to be done to implement the software. So how the software is going to be implemented. And that is more of a software specification. So here's an actual outline that you can use for a requirement document for software. It's not comprehensive, but it's a pretty good outline. It has three parts. It has three main parts where the meat of the document is sort of part 3, which is on the next slide. But you have some usual suspects like the software product, the name of the manufacturer, version date, things like that. Some type of introduction part, where you cover things like purpose, what the software effort or product covers. If you have a specific terminology, it should be explained in this section. If you have references to other documents, it should be here. So referencing documents is much more advisable than repeating information, because every time you repeat something, if your source changes, then now what you have in there becomes stale. So it's better just to reference. And these tools of managing software documentation or software specification can very easily link to other documents. So you have basically a dynamic documentation of what the software is. So that would be in this section, as well as an overview of how the document is structured. Then you can have a general description of the product. So how does it relate to other products? Does it need to work with other products? Is it being built based on other product, or is it something totally new? A summary of the features, and also a summary of the expectations for the user. If this software is something that to use it, someone needs to have certain level of education or training or know-how, or is it something, a general software that you can give to anybody and expect it to use it? Those are different type of usage or use case constraints. What type of limitations? Do we have limitations on a specific hardware? So a lot of embedded system, we have limitations on hardware, so you would have to specify something about that in this section. Assumptions on dependencies. So what are the restrictions? Are we restricting to a specific operating system, or do we have to cover multiple operating systems? And also, what are the requirements to distribute the software? So all that should be in this general section. And then comes which is the most important part, the specific requirements. This part 3 of the document would be the specific requirements. Again, functional requirements and non-functional requirements. Within this part 3, these two actually would be the most important part. But there are other very important parts in this section as well. External interfaces and the design constraints. And what are the non-functional constraints and performance requirements, and also quality requirements. So from a quality perspective, what do you expect the software to have as it is implemented, and then basically any other requirements you can have in there. So this is the most important part of the requirements document, but this is an actual outline that can be used, and it's pretty succinct. So to summarize, if you're going to implement successfully complex software, you should have, at a minimum, visibility and implementation of these core processes. You should be doing requirement analysis, and after you have that, you should be doing some prototyping. You should be doing the actual architecture and design of the software with whatever knowledge you gain from the prototyping exercise. And it is during the actual architecture and design that what the customer wants, the customer requirements, and what can be done gets reconciled. So there can be some iterations between these 3 bullets in this list. And when you have a firm architecture and a design, so you know you have a clear vision of how you're going to implement the software, how is it going to be, the problem is going to be tackled, then it's a matter of execution, which may take the longest time, but it's not necessarily the most complex or critical part. So this part of just programming, doing the testing, the validation with the actual environment in which the software is going to be operating, and also from that you do a release and you go into your maintenance schedule. So these processes are the minimum that you should have to have a robust software development enterprise. Still, within these processes, we have to go back to the V model and the waterfall model and the agile approach and recognize that traditionally, when we develop software and we test it later, and you're making a lot of assumptions during the architecture and design phase. And that's when you're making the decisions, because after that it's just the implementation or the execution of the project. So if you made an incorrect decision or not the best decision, you don't find out until later when you are going through that validation phase. That's a long time away, because remember that what takes the longest time is the execution or the actual implementation of the software. So another way of tackling this issue is to shorten that, to bring into the architectural phase, bring in modeling. So you can actually start validating through modeling without having to actually write something, using tools that allow for rapid model-based, system engineering-based, and modeling-based prototyping, trying to see if the decisions, the architectural and design decisions that you made during this iteration of formulating the requirements are feasible. Are they good ideas? Are they a good way to tackle the problem of producing this software? So by bringing modeling forward, you start doing a lot of your validation early on. So you don't rely on downstream testing solely to see if you made good decisions. You're bringing in modeling to the forefront. It shortens the overall execution time of the project. So this diagram, or this contrast of diagrams, is one of my favorite, because it shows on the left kind of like the classic way of doing things, where you do requirements, you start doing some preliminary design or architecture, and then you go into detailed design. And this is where the major decisions are made. But if there are erroneous natures to those decisions, you find them down here. And that's a long time away. So this shows what I was saying. So during the requirement phase, you start bringing in modeling. And you don't go forward with your design until, through modeling and rapid prototyping of the system, you can prove that you have a high likelihood of meeting the customer requirements, of your validation being successful. So then you go through the system architecture and implementation, and of course test and validation. But then this becomes much shorter and more efficient. So one of the last things that, I started today saying that I'm actually going to finish the course today from a lecturing perspective. We are almost at that point. And I also said that in looking at chapter 7, I'm comfortable with doing that because we discussed manufacturing in the context of cyber-physical systems a great deal during chapter 3. So I am comfortable on essentially assigning chapter 7 as a reading assignment in which you will write a paper on it on chapter 7. a short paper like the one that you wrote for the presentation that you went for Professor Abbas. So I'll put that assignment on Canvas, but from a lecturing perspective, I'm going to stop right after this chapter 6, which we're almost over with. Then basically we will not, I have an appointment tomorrow. We will not have a lecture tomorrow. But on Monday, we will be here and we'll be doing review of chapter 6, which is going to be on the final. So it's going to be very important. A lot of chapter 6 is going to be on the final, because being about systems engineering and software engineering and how it relates to cyber-physical systems is a very important chapter from my perspective. So we're going to do that on Monday. Then after that after the break is the last week. We're going to review overall what we're going to do for the final. You should be wrapping up your projects, and then on that Thursday, the last Thursday, we'll have the presentation. So that's how things are going to play out through the end of the semester. Okay? So, so dovetailing from this diagram, and given that we are wrapping up the chapter and the course, I wanted to actually show you something of what we have been talking about. We're using MATLAB not only going forward in the systems engineering course, but I'm being a very vocal proponent of you guys using Simulink for your project. So this is a real life Simulink early model, like the one that I just talked about, of a high speed radar system that is meant to not only detect speed and direction, but also detect the shape of cars. And so it has a lot of applications to autonomous vehicles, because radar uses microwave, and microwave can see through obstacles, fog, and different weather conditions that visible light camera computer, classic computer vision cannot deal with. So if you have rain and fog and things like that, smog, whatever, computer vision becomes difficulty. You can use LiDAR, but lasers are very expensive. And if you're putting a lot of these sensors around autonomous vehicles, then it becomes very, very expensive. So this is an inexpensive alternative to laser-based sensors. So you could actually apply computer vision techniques to the information that you get from radar, and again, it can see through obstacles. So this is a model of such a radar, and it's just one part of the functionality, the basic, can it detect the speed. But one of the things that we have been talking about is the attractiveness of being able to deal with real-time data. So what are we doing here? We're actually bringing in data from an Excel spreadsheet of the actual data that is being collected from actual cars. And this data is thousands and thousands of data points. It's huge. And for this, I cut this to 70,000, which is essentially half a minute of data. So you can imagine. So, but the point is that you are bringing in real data. This is not from a synthetic target in a lab, which we have. So we can have targets that mimic a car, and we put it against the radar, and the radar thinks that it's a car. But this is a synthetic target. That's a much more controlled environment, and you don't get the benefits of having real-time data. So you collect this data, just reading from the analog to digital converters, and here we have the I and Q, which are the in-phase and quadrature components of the IF, the intermediate frequency of the sensor. And here we have a synthetic ramp type of waveform, just like we have in the embedded system, that modulates the carrier, the microwave carrier. So this is a K-band type carrier, so this is about 25 gigahertz. But it is basically, this ramp modulates the FM of that carrier. So frequency goes up, frequency goes down in an FM way, and the amplitude of that ramp gives you the bandwidth. So in this case, there are some parameters here where we calculate some things. And for example, you should recognize this big number here. That's a billion. It's converting to gigahertz. But we are around 24 gigahertz, and we're modulating from only about 8 volts to 10. So only 2 volts of modulation. That's not a lot. That's not a huge bandwidth. If we have more, we can modulate this to 12 volts and expand the bandwidth, and you get more information because you're not crunching the spectrum. So anyway, we get the, well, I'm not going to go through every go into detail, but you get the data and you frame it. So these are framing buffers, and then you do something that is very necessary when you're doing radar detection, which is you mix your reference, which is the synthetic reference, with the actual signal, and that's being done over here. Also, since we're going to be implementing this in an embedded system that has specific requirements for example, you cannot just do floating point arithmetic because that's very expensive. So if you're doing fixed point arithmetic, you have to at least model the effects of that, the scaling, and how you get rid of the DC components. So that's being done in a subsystem here, okay, which you can basically drop down into and see that and go back. And after you mix, essentially you take an FFT, okay? So you look at the spectrum, and once you have that spectrum, you manipulate it to get rid of the DC component, you get rid of the fundamental. So here, for example, this 0, we are suppressing the fundamental out of the spectrum. And then you basically look for the peaks. And those peaks gives you the Doppler shift that gives you the speed of the object. So to look at the peaks, we're doing sorting and just selecting a couple, the 2 major ones. And then that feeds the inverse radar equation, and here you get a speed, okay? So if I run that, and if you see that the spectrum is going to jump, and you're going to see the spectrum moving, and that's actually a car going by, okay? Or a couple of cars going by. So if I run this, you should see the spectrum moving, okay? So you see that it bounced like that? Well, that's basically a car went by, okay? And so just by one click, we were able to simulate half a minute with real data of what. So this gives us a lot of insight. I can go back to the workspace here and look at the speeds and see that, okay, these are very low, so that's essentially 0. That can be, but over here, you saw that those cars going by, 60 and 30 here. Those are the speeds, miles per hour. And then we can see artifacts like, at some point we're dividing by 0, so we can look at things like that and say, well, that we need to get around that. We shouldn't be dividing by 0. So we can, we're dividing by 0, so MATLAB is very gracious and sticks a big number in there. That may not be so good in an embedded system. It may not handle it very graciously. So you may have to put some checks to make sure that you don't divide by 0. So So anyway, that's what I wanted to show you, like a real system and what it might look like from a simulating perspective. Okay? So as we wrap up the chapter on systems and software engineering, there are other things beyond just the process of doing the software. There are tools for all of this. There are the processes of managing the requirements, managing the actual implementation, so doing the project management, managing the quality aspects of the software and the quality infrastructure to deploy the software. There is configuration management, so different versions, different stages of the development, how different developers communicate and pass this and are working off the same source and things of that nature. There is the important issue of documentation. And finally, defining training. Training, if there is a specific training to be given to the customers that are going to be using the software. So there are a lot of infrastructure and tools to develop software. I have some of this here. I just wanted to highlight from the perspective of cyber-physical system. An interesting one that uses service-oriented architecture is the SCADA DCS. So SCADA stands for Supervisory Control and Data Acquisition, and also the distributed control systems. These are software infrastructures that run on top of operating systems, and on top of this infrastructure you have specific applications, and they are used to manage complex data acquisition sensory type systems. They are used, for example, in your power plants. They will have a SCADA type infrastructure deployed, or the big manufacturers of semiconductor chips. They will have SCADA based instrumentation and sensing, so to know if they have all the different poisonous gases they use to make semiconductor chips, if they have those under control, there are no leaks, so all kinds of sensors and safety protocols. So that's an interesting one. I think that the rest of them you are familiar with in terms of tools, frameworks, and different programming languages. So with that, we pretty much end chapter 6. So we started with an introduction to systems engineering. We talked about design challenges in cyber-physical systems representation, and how systems engineering discipline, or the system engineering discipline, coupled with topics and techniques of software engineering, could be applied to requirements for software in complex or in cyber-physical systems that are complex in nature. So that's the end of chapter 6 and the end of the lecture. So we covered 6 chapters. We started with an introduction to systems, and then we talked about embedded computing system as an essential element and a premise for these complex cyber-physical systems. And then we had a chapter on cyber-physical system where we talked about how to sense, control, and all the different myriad of applications that are possible for this cyber-physical system. So complex computing systems that are connected, that are networked, and can serve a number of applications. So we saw a number of applications in that chapter. Then we also discussed the Internet of Things paradigm as essentially an infrastructural bed for these cyber-physical systems that would allow them to connect together and collaborate and make up these complex systems, which led us to talk a little bit about pervasive computing. Now that we have all these complex systems together, if they have a surplus of utility, they can actually be used as a pervasive computing environment to do all kinds of novel applications. And then we came back full circle to talk about systems and software engineering in the context of cyber-physical systems. So that is pretty much from a lecture perspective, the course, and I hope that you enjoyed it. And we have a lot of some other things to do over the next few sessions, and I'll repeat those shortly. But from a lecturing perspective, that's it. That's what I'm going to cover. So again, thanks. I hope you enjoyed it, and I'll see you next time. Okay? Thank you.